This is a great word problem with practical application of some of the stuff that we've been learning. And I'm just going to start off by a little bit of a reminder that if I have a function that is a position function, it is usually written, we write the function s is a function of t. Position is a function of time. That's position. And then s prime is velocity. And the second derivative is acceleration. And I like to think of these as kind of in this format, like top to bottom. That kind of helps me remember, where they start. So I am told in the beginning of the problem that on the moon, acceleration is 1.6 meters per second squared. So let's write that here. 1.6 meters per second squared. And the first question says, A says, if a rock is dropped into a crevasse, I think that's how you pronounce it, like a canyon, how fast will it be going just before it hits bottom 30 seconds later? Well, how fast is velocity? So I can see that I'm going to need to go up one level. And I know that if this is f of x, and I'm going up a level, I want to find big f of x. In other words, I want to find the antiderivative of acceleration. Antiderivative of acceleration. All right. So I know that acceleration is equal to the second derivative in relationship to t, and that is equal to 1.6 meters per second squared. And I want to find velocity, which is s prime of t, one level up. So I'm going to use the antiderivative. And I'm going to say, well, this acceleration is really the same thing as 1.6 x, or t to the 0 meters per second squared. Because acceleration in this case is constant. It's not a function of t. It's just a constant. So I'm putting t to the 0 so that we can see more clearly how this antiderivative works. So the antiderivative would be 1.6 placeholder t to the first. Well, the reciprocal of 1 is 1 over 1, so I have 1.6 times 1 over 1 t for the velocity. So really what I have here is I have 1.6 t meters per second. That is the velocity function. I went up one, I got the velocity function. Well, what I need to find is s prime of 30 seconds, right? That's our t. It says, how fast is it going 30 seconds later? Well, that would be 1.6 times 30 meters per second, and that's equal to 48 meters per second. That's how fast it is going after 30 seconds. So that is our answer to part A. Part B says, how far below the point of release is the bottom of the crevasse? Well, I know it took 30 seconds to hit the bottom of the crevasse. And what I'm trying to find, where it says how far below, I'm trying to find the position function. Well, to find the position function, I may need to find the antiderivative of the velocity function. So, let's go down here. If my velocity function is s prime of t, and that is equal to 16t meters per second. The antiderivative, I'm going to find that by doing this. I'm going to go, so the antiderivative would be s of t, the position function, we'll call that position, POS, is equal to, well, I'm going to go 16 times my placeholder. Now this is t to the first, so it's going to add 1, t squared, and that's just going to be meters. Okay, not 16, 1.6. 1.6. I'm sorry, I forgot the decimal point. So that's equal to 1.6 times the reciprocal of our new exponent, 1/2 t squared meters. So it's equal to 0.8 t squared meters. That's our position. And what I'm trying to find is s after 30 seconds. So that is equal to 0.8 times 30 squared. It's going to be in meters. Let's look at the calculator. 0.8 times 30 squared, 720 meters. So the bottom, so S of 30 is 720 meters. So the bottom of the crevasse, part B here, is 720 meters. So we've gotten A done, and we've gotten B done. Now part C says, well, I'm not just releasing it from rest, I'm actually throwing it down with a downward velocity of 4 meters per second. When will it hit the bottom? And how fast will it be going when it does? So I'm going to need to find T, and I'm going to need to find V, velocity. So this right here was my function for velocity when I let it go at rest. But since I'm throwing it down with an initial velocity of 4 meters per second, it's going to be that plus the constant 4. So my velocity equation is this right here, 1.6t plus 4 meters per second. I need to solve for t, but I don't know how fast it's going. I don't know how long it's going for, but I do know the position at the bottom. And it's asking me how fast is it going? How fast will it be going when it hits the bottom? And I know the bottom is 720 meters down. So I can look at this, and I need to find the antiderivative of that. So position equals S of t, which is equal to this. I have my 1.6 placeholder, t squared, because I'm adding the 1 here, so that gets me t squared. This is the same as t to the 0, so I'm adding the 1 there and put the placeholder there. So my antiderivative to find the position function when I've thrown it down at an initial velocity of 4 meters per second is going to be 0.8 t squared, because this is going to be a 1/2, this is going to be a 1 over 1, plus 4t meters. And I happen to know that to the bottom is 720 meters. So, how much time is it going to take to get to 720 meters? I can figure that out by setting this equal to 720. So now I know my position, because my position is 720 meters down. This is the function that describes the position. That's going to tell me how much time it took. Then I'm going to plug that time into the velocity function. But let's just do it here. I have a quadratic here that I need to solve. So I'm going to get everything on one side and set it equal to 0. So I have 0.8 t squared plus 4t minus 720 equals 0. Well, I don't like decimals, so really what I'm going to do is I'm going to divide everything here by 0.8. Divide that by 0.8, divide that by 0.8, divide that by 0.8, even though it still comes out to 0. And what I end up with is t squared, excuse me, plus 5t minus 900 is equal to 0. Well, I have no idea how to factor that. 900 is too big of a number, so I'm just going to jump right to the quadratic formula. And I'm going to start with my discriminant, which is b squared minus 4ac. So that's going to give me 5 squared minus 4 times 1 times negative 900. And that is equal to 3,625. So it's a positive number. I'm going to have 2 real roots. That's good that it's not a negative number. So the full quadratic formula is negative b. So negative 5 plus or minus the square root of my discriminant, 3625, all over 2a, so that's 2. And if I plug that into my calculator, I get approximately 27.60 seconds. So that's my t, that's my time. Now, I want to know what my velocity is. Piece OK. I just go back up to my velocity function, which I got as the antiderivative earlier. So it's velocity equals 1.6 times the time, which was 27.60, plus 4 equals 48.17 meters per second. So it takes 27.6 seconds to get to the bottom, and at the bottom it is going at 48.17 meters per second.